Okay, so this was the last slide for the last lecture, right? We discussed encoder, the concept of encoder. What a decoder does is it takes a set of inputs and it creates one of the outputs activated at the time, right? Or deactivated, depending on whether it's a true or inverted type of decoder. Give me 1 second. Like always, this guy has been acting weird, but should be okay. All right. So, but an encoder is exactly the opposite. So you have a number of inputs, only, I mean, based on which input is activated, say this one or the other one or the other one, depending on which one is activated, you choose a specific code for the output. For example, let me show you. If this row is activated, say for example, y0 is 1 and everything else is 0, then you show 0, 0, 0 at the output. Make sense? Okay, now consider not the first one, but the second input, y1 is activated, meaning 1. Then what you show is, you show basically, if you consider A, B, C, from most significant bit to least significant bit, you show 0, 0, 1. So C becomes 1 and everything else becomes 0. Right? Isn't that logical? Isn't that exactly the opposite of a decoder? Right? As we discussed in the last class as well. There is just one catch here. That is, inputs, there is a possibility that multiple inputs could be 1. Right? For example, what if y0 is 1, y2 is also 1, y4 is also 1, blah, 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 right? Then what do you do? How do you handle that? Because inputs are often driven by, you can decide on the output. You can design the circuit in a way that it only provides a certain type of output. But how do you control the inputs? Because oftentimes the inputs to a circuit comes from other branches of the circuits. Does that make sense? So you don't always control that, hey, we will always end up with just one input to be 1 and everything else will be 0. There is a possibility that multiple inputs could be 1. So that's why, notice marked this term here. It's called a priority scheme. It's also known as a priority encoder. It basically prioritizes. It prioritizes the higher number. For example, what I mean by that is, if y4 is 1, you don't care that y0 was also 1, y2 was also 1. You don't care about anything else. You just treat as if y4 is 1 and everything else is 0. So whatever is the highest number that you get. Am I making sense? So you see that from the truth table here as well. If y1 is 1, you don't care about what happened before it. You just treat, and this is the highest. Okay, notice, say this example. Here, y4 is 1. Maybe y2 was also 1, y1 was also 1, but you don't care about any of them. You just look for the highest number that becomes 1, and you act accordingly. Right? So it's all the same if only y4 is 1 and everything else is 0, or everything up to y4 is 1. You just respond based on the highest number that becomes 1. Are you all with me so far? So what if there is a situation where y2 is 1 and y5 is 1? Who do you look at? Do you look at y2? No, you just look at y5 and you create an output combination that represents 5. That's all, y5. Are we all on the same page? That is the only difference to keep in mind. You have to do a priority logic incorporation to make sure that you can handle multiple inputs to be simultaneously 1. Now, one other minor difference, which I kind of pointed out in the last class and I asked you to think about it. Did anybody get a chance to think about it? Can anybody answer why we have an extra input? So in a decoder where we had like 3 cross 8, you had 3 inputs and 8 output. In an encoder, basically we are still calling it 8 to 3 priority encoder because it decides on the priority, of course. But yeah, we are still calling it 8 to 3, but you don't have just 3 outputs, you have 1 extra, right? Why is that? Can anybody guess or help answer? Yes.
So it needs to know when it's either a 0 or a 1.
Yes. So thank you. I think the answer could be easily visible from here. Notice the output D is mostly always 1, except for one case. That is when all the inputs are 0. Notice, I'm portraying an encoder as a circuit that creates creates an output based on which of the inputs is activated. Okay. So if y0 is 1, do something. Is y1 is 1, do something else, and so on. But what if there appears a situation where none of the inputs are activated? Like none of them. Remember, when the first row is activated, you are already choosing 0, 0, 0 at the encoder output. So when none of them are activated, what do? Basically, you still show 0, 0, 0. So you have the same output combination for two possible inputs, which is confusing, don't you think? So to differentiate between these two situations, you create an extra output, which shows it only becomes 0 when all the inputs are 0. It's as if it's like an useless situation for encoder. I mean, we still have to create a output to keep track of. It's like a flag that shows whether you have any input at all. If there are no inputs, everything is 0, then this flag becomes 0. Otherwise, this flag is always activated. Does that make sense? So you see, special situations in logic design require some additional tweaks. That's all. So other than that, encoder is exactly the opposite of a decoder. And I don't have to tell you, the name tells you encoding and decoding is a very important part of our digital universe, as you see, in terms of cybersecurity, maintaining your passwords and making sure your password is correct and whatnot, right? This is a heavily used circuit. So whatever circuit topologies that we have learned so far, all of them are building blocks. So they're heavily used across digital universe. Okay, so with that, I'm going to move over to the new lecture today, which is on programmable logic devices. Before I move on, any questions? Okay. So as the name suggests, typically the names are self-explanatory. We will talk about some specific circuits and devices that are programmable. So you don't predetermine the function, the Boolean function that will be implemented. You create them in a way that they're general purpose, and you can program and reprogram them over, different situations. So that's what this lecture is gonna be about. We will start with something that is very preliminary, very simple, plain vanilla, and then end with something that you will be using in this course for your labs and project as well. And it's not just for the sake of the course. That thing that we'll talk about, which is called an FPGA, as you can imagine, is heavily used across the board in digital universe. Okay, so let's start with the concept of programmable logic array. Okay, let me stop here before I go through the slide and ask you a question. How many of you remember SOP, sum of product form, in a Boolean function? I hope all of you, right? If not, if not properly, at least to some extent, you should have this sense. So if a Boolean function is expressed this way, ABC plus DE plus GH, something like that, where you have a bunch of product terms and eventually summing up those product terms, that's the sum of product. And this is a universal format, which means that any Boolean function could be, let me, okay, now it's okay, now it's working. Any Boolean function could be represented using this approach, right? That is the most important part. So what this programmable logic array does is it creates a way for you to implement any sum of product expression. Sorry, my tab is acting weird for some reason. Sorry about the distraction. So what it gives you is you have an AND array. So you have two arrays, two blocks of arrays. One with just AND gates and the other one with just OR gates. Okay, which basically, as you can imagine, is targeted towards implementing sum of product. You incorporate the product terms using the AND array, and you incorporate the sum term using the OR array. And this could be programmed based on, I mean, let me show you an example. I think this is much easier than the first slide. Let's talk about it first, and then we'll move back to the first slide again. Okay. Notice that you have 3 inputs without any loss of generality, right? You can have as many inputs, for example, but depending on that, the overall array size will increase and complexity will increase, of course. So for the sake of the example, let's consider that you have 3 inputs, A, B, and C. And did I tell you in one of the previous classes that we typically always assume that every input also is available in its complementary form? If not, we create that complementary form just for the sake of it, in case we need it, right? So that's what you see here, another signature of that same argument. You have input A, and you create a separate line with input A prime, basically, another literal of input A. Okay, same applies to B, same applies to C. So you create three data buses, basically, with 3 inputs and their complements. Okay, and then say, for example, if you route them vertically, you have a set of interconnects, and I'm going to use this term. I hope I used it before as well. Interconnects are essentially metal lines, and in chip design, you don't just randomly draw lines like we would have drawn in a conventional circuit, right? For example, when you are trying to draw a circuit on your paper, you could just draw in any direction, in any shape or form. But in practice, when you make this chip in hardware, you have interconnects that run horizontally, always parallel to each other, and vertically. And you have layers. One layer might run only horizontally, and another layer will only run vertically, and so on. We try to crisscross them in a way that you could come up with grid-like structure. Okay, just getting ahead of ourselves. Sorry, give me 1 second to restart PowerPoint because it's giving a lot of trouble. So let me restart this. Okay. So when I try to switch over from, oh yeah, still doing the same thing. Anyways, I'll figure it out later. Maybe some kind of software update messed it up. Okay, so it's not letting me erase anything. So I have to go back and forth. And all right, so notice this is your AND array. You have a set of AND gates, and this is your OR array where you have a set of OR gates. And can anybody tell me that have we seen this type of a structure before? Right? When we started learning about implementing Boolean logic in circuits, this is the first type of circuit that we learn. You have a set of AND gates followed by a set of OR gates, because that's sum of product, right? And I told you that this is not the best way to implement. We eventually learned about NAND and NOR implementation, but this is basically the basic, the foundation of Boolean logic design, right? And this hardware, this programmable logic array, basically mimics the foundational Boolean logic design approach. Okay, so imagine you are trying to incorporate a situation where you have multiple output. So F0, F1, F2, F3, your output. And every one of them has a specific agenda. For example, F3 has to be B plus AC. Okay, so how do you incorporate? I'm going to show you a couple of this, implementations so that I don't know what to do, honestly. It's like, okay, now it's showing up. Okay, let's see. Clear mark. Okay, now it's working, thankfully. Okay, so F3 is B plus AC. Let me start with that. Okay, so I need 4 outputs. I will be using 4 OR gates eventually. Okay, 4 outputs, 4 OR gate. Every output comes out of 1 OR gate. Keep that in mind. Okay, so considering F3, what do I need? I need B and I need AC separately, because look at the plus. This OR gate is going to do the plus stuff, right? But before that, I need the other things. So first, I need B. And notice, this is my input B. It is going through an AND gate with just one input because I'm not using the other input. You see my point here? And it is getting into this OR gate. How about AC? So to incorporate AC, I need input A and I need input C in their actual form. And then I'm going to take an AND between the two. This is the AND gate, and I will get AC here. And then I feed this AC into the OR gate. That way I get B plus AC at F3. Any problems so far? Yes.
Is the B gate even necessary?
It's not. So this is just an example where, imagine this is a general purpose hardware. When you sell this, when you make this, you don't know whether you need just one input or two inputs, right? So I don't really need this gate at all, but it is there. So basically the reason why they're called programmable is because they make a bunch of the same hardware for you to program later. So for your unique case, maybe you have a situation where you have just one input B. So you don't need that AND gate, but you just make the other input 1 or 0 to make it use like to use it like a buffer essentially. Okay. Okay. So what? Let's take an example of another input, say output F2, A prime B prime plus BC prime. I hope it will make sense. So this is A prime B prime. So we need two things here. I need A prime B prime and I need BC prime, which is here. Now, how can you make A prime B prime? You take the primed version of A and you take the primed version of B and you use one of the end stages to create A prime B prime, and then you feed it to the OR gate. Isn't that very straightforward, folks? So take a step back and track each one of these output, and hopefully this will make sense. Okay, so that's exactly how you design any random output. Remember, when we started discussing our Boolean logic design, we started with multiple inputs, one output. And we even went up to designing K-maps with just one output. Then we introduced the concept of having multiple outputs in the same system, right? So what this shows you that you can incorporate functions with multiple outputs and multiple inputs, of course. I mean, what is the use case if you don't have multiple inputs? Because you need combinations, right? So you have multiple inputs and multiple output. But there has to be a measure of how many output you can handle with a given hardware. Imagine I give you like 12 output OR gates and 12 inputs. How, what is the maximum complexity of the Boolean function that you can incorporate? Are you still with me? Okay, so as you can see, every OR gate gives you an output. So obviously, if you have M output lines, you need M OR gates essentially, right? And also, if you have N input lines, you need you need enough N gates to handle that combination that N input line gives you, which is 2 raised to N. All right, so that's what this slide also talks about. Basically, the number of input lines and the number of output lines matter. And when people design this PLS, they design it based on a certain number, which is relevant to the application domain. If you need more complex Boolean logic, then you can no longer use it. You have to move on to something more complicated, right? Okay, and one other thing is this could be an interesting testing ground for your logic systems, but it is not the most efficient, because if anything, you must know that incorporating logic in this format is not the most area efficient thing to do. It is obviously not the most energy efficient either, okay? Because you are basically distributing it across a set of array. Most of it is unused. You don't really, this was a classic example. You just had a one input that you had to channel, but you are using an AND gate for no reason for this. Okay, and that is the signature of most of these general purpose programmable platforms. The programmability and universality comes at a cost of not having proper optimization. Okay, that's called basically when you go for ASIC, application specific integrated circuit. So your circuit, your integrated circuit IC is designed specifically for the application that you're doing. Let me take a step back and give you an example here. Imagine Tesla, they're using a dedicated chip that is designed and built for self-driving. Okay, so it is specifically designed and optimized for the task that is meant to do. Now, when you if you try to resell that chip for gaming or to play a movie somewhere, right? It will not be the most optimized thing. As opposed to that, imagine when Intel sells Core i7, they don't know whether you're going to use it for watching movies, writing an essay, running games, whatever, right? It's a general purpose processor. So when they try to make sure it is a processor which is programmable like this. This is the easiest possible programmable system that you are ever gonna encounter, the one that we just covered. And on the other end of the spectrum, there is these processors, microprocessors, which are like super general purpose. You could use them for almost everything. Okay. So remember, that is also not the most optimized situation. So that's why if Tesla buys a Core i7 and just puts it out there and use it for uh, autonomous driving, it's gonna work for sure. It is general purpose, but it will not be the most efficient, and it will spend more energy than necessary. It will be slower than necessary. Versus if you design it, basically custom design it for specifically that purpose. Okay, I mean, taking some real example from devices that we use, Apple, for example, they have a dedicated chip for fingerprint reading. I mean, some of you who have like maybe MacBooks, they have a dedicated button and there is a chip on board. Why do you have a separate chip for that? Why can't you use the built-in processor? Because they want to make sure that the pattern that you store, it is locally stored. I mean, your fingerprint will not be sent to a server and stored there and compared against that information. Because if there is a hacking in the server, they can get access to your biometrics, right? So if it is locally stored, it's safer. So that means you have to find a way to create a logic system that compares your stored information, which is there in the hardware, with whatever you're providing as input. So what I mean by that is that particular chip is optimized and designed for biometrics testing only, right? So it is really optimized, lower energy, more efficient, and natural. But if I use a general purpose processor, it's never going to be as smooth and optimized as this. So remember, the more general purpose a hardware is, the less efficient it will eventually become. What is the use case then? Can anybody guess? Why would Intel go for? I mean, this is not just Intel, right? Most companies have a general purpose version. AMD has their Ryzen, for example. So why would people create this general purpose stuff? Because when you mass produce, that reduces cost. It significantly reduce cost. You make like 10,000 Core i7 processors. You don't know what they're going to be used for. You sell it to the gaming industry. You sell it to, Oak Ridge folks for their supercomputers. You sell it to students so that they could write essays and, work on their homeworks, whatever. Like you have all sorts of applications coming out of the exact same hardware platform that you design once and make in bulk. That's how you save cost. So general purpose platforms will have lower cost. Okay, all right. Now, imagine if you're trying to deploy a system in a in, in a hardware that is extremely cheap. Like for example, an agriculture sensor. You're gonna create them in bulk, like 10,000 of them. You're gonna throw them around in a field for sensing or controlling some stuff. You are definitely not gonna use Core i7 processors, are you? Okay, every Core i7 will take few $100, and you need like 10,000 of them in your cornfield. Like, of course, you're not gonna do that. So all you need is sense whether there was a rain or not, for example, right? There's just one thing that you need to do. So why don't you use a system like this, which is super cheap, super like primitive, of course, easy to implement, but you don't really need to change the world with this thing. You need to incorporate systems that are targeted, small scale, and needs to be cost efficient because you need many of them and they scale up. And this is just one example. Agricultural sensing is not the only example here, right? There are many examples around us that require a toaster oven. You're not gonna, sorry, like maybe a small toaster that you're using to, toast your breads in the morning. You're not going to use a Core i7 for that. It's definitely going to be an overkill. You need a small scale system that has some logic. Okay, what is the temperature range? What is like the timing, blah, 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 right? There are a few inputs that you provide, and then it decides on the output based on the logic that is programmed. Your toaster oven will never be programmed as something else later on. It's always going to be a toaster. So the logic never changes. So if you could reduce the cost by going for a primitive hardware like the ones that you're seeing today, PLA, PEL, which is coming up right now, these are all primitive version of logic, but they're still used. Remember that. And FPGA is probably the higher end, basically the higher end of these primitive logics. And what is more general purpose than FPGAs? General purpose processor, which is more complicated, extremely difficult to teach in a course, in a university setting. Of course, nobody learns everything about a processor. That is by design. Intel, AMD, they don't want one engineer to know everything, because if you do, if you change the company, there goes their IP, right? You will only know a small portion of the overall architecture, only a small portion, so that you become an insignificant, by design, insignificant part. Even if you choose to go to a different company, they don't really lose out much, because there are more engineers like you who have small pieces. That's why they have many engineers. So that's a very different ballgame. You'll never be taught about the full-fledged processor architecture in a course. You only learn about it by working in an industry, in a setting that is higher up enough. For example, the CTO knows a lot about many pieces, but an engineer knows a lot about a small section of the process, because engineers change jobs all the time, but CTOs changing job is not really that common. Anyway, sorry, it's a tangent, but are you still with me? All right. So we covered PLA. This is an example of a PLA realization. One more example. Basically, we covered an example here. This is a simplified version. What it shows you is that you don't have to necessarily show the AND gates or the OR gates when you design or draw these PLAs, because they're just gonna sit there, right? So oftentimes this is a customary, way of drawing things. You only show the connections. You assume that there is an AND gate sitting here. Okay. So how do you read it? See, this is A prime because it is coming out of this inverter. This is B and this is D. So what you have here is, in this line, you have A prime BD. See, I'm not showing you any AND gate at all. It is much easier to draw and quicker to draw. Like I can show you one of this as an exam question, for example, and ask you to come up with the final function F3. How do you do it? Let's do it together in class. All right. So let's see. What is F3 made out of? This line, what is this line? Can anybody tell me what is this? B and C. So this is BC. Oh, is that the only thing that F3 has? No, look at the dots. There is another one. And if you go through the chain, you'll see A, B prime, C prime. There is another dot here. You have A, B, D. So F3 is essentially what? BC plus A, B prime, C prime plus A, B, D. Isn't that easy enough to handle? Okay. All you have to do is track the dots. That's all. All right. Now, moving to the next example. PAL, programmable array logic. The sound, it sounds similar to what we just discussed now, PLA, because they are basically same, except for one difference. A PAL, or programmable array logic, also has AND and OR stages, but only the AND stages are programmable. Remember, here your AND stages and OR stages were both programmable in a PLA, but for PL, this one, the OR stage is not programmable. Okay, by design, we are just basically trying to reduce cost. Remember that. The more programmability you incorporate, the more costlier it will become eventually, and also it will take more space to. I mean, what you didn't ask me about, how do you program this? I'm assuming that this is granted. This is like, okay, given. You could always program this interconnection, but there is a separate type of logic incorporate, a logic that is necessary to be designed to have this interconnects programmable. All right. So I'm not getting into that degree of detail for this course, of course, but for here, you're just assuming it is given. Okay. So by getting rid of programmability in the OR array, you're significantly reducing the hardware complexity. That means you're significantly reducing the cost. Okay, just keep that in mind. How can you handle that? Let's just directly jump into an example here. When you see this open-ended circles, that represent it has not been programmed. So it is unprogrammed. And when you see this crosses, that shows that it has been programmed. Okay, so let's see what this hardware is implementing. And notice your programming is only happening in the AND array, not the OR. So the ORs, this is the, let's do one thing. Let's look at the final example together so that the previous one will be like a toy. Okay. So let's start with this one. So this is essentially a full adder implemented in a PAL fashion. Okay, let's do it. So for a full adder, I hope you remember that we looked at the full adder in your lab as well as in a lecture as well, but we used A, B, and C in as input. So this is taken from textbook, and they have used X, Y, and C in. So without any loss of generality, X and Y are like A and B, of course, right? So this is, as you know, a full adder has two outputs, sum and carry out. So this is the expression for the sum, as you have seen many times, I hope, during your lab and in the previous lecture. And this is the expression for the carry out. So I need two outputs. And these two outputs will come from OR gates, OR gate and OR gate. Notice these OR gates have 4 inputs each. This is a design decision. You may not need 4 inputs. You might need just 3 or 2, but the others will be redundant. Am I making sense? You make those inputs static, DC, so you don't really use them. But you have to live with the number of inputs. Now, what if I need 5? You cannot. That's your limitation. That's a design choice. Okay. So let's track just one of the inputs, say C out. So how many inputs do you need? 1, 2, 3. You don't need 4 inputs for the OR gate, do you? You need 3 input. So you have 1, 2, and 3. And notice the other one has been crossed out because this is inactive. It's not being used. You can use only the 3 inputs of a 4 input OR gate. It's fine. The other one is like unused. Okay. So among these 3 inputs, you need X, C in. Let's see what this thing is doing. This is, you see that this is coming from X, right? And also, so X and C, let me see, what is the other one? This is C in. So this row is giving you X, C in. Does that make sense, folks? One thing that I haven't told you about is, what is this symbol? This is just a symbol that the textbook decided to use. Remember in the previous slide, we used to show true and complementary version of the input this way. You have one line and you have an inverter giving you the inverted version of it, right? There is an easy way to express this input buses, which is this symbol. You use an inverter, you have an input, and you show an output coming from here, which is essentially the same input, and you have an, sorry, you have an inverted output as well, input bar. So that's how we typically show this bus. This is exactly the same thing as we saw before, all right? Make sense? So what it represents is you have both X coming out of this line and X prime coming out of the other line. That's all. Are you all okay so far, folks? Okay, so the first line incorporates X, C in. And you'll see the second line, and you can easily track down where it is coming from, whether it is Y or C in or whatever, right? Let me do one of the examples for the sum function now. For the sum. And I'm going to take maybe the first example, first row. So you need 4 inputs, 1, 2, 3, 4. That's why all 4 inputs are being used. Okay. So for the first input, you need X prime, Y prime, and C in. So let's see whether we are getting that. What is this cross coming from? You see that it is coming from the circle version of this output. So this is essentially X prime. Okay, makes sense? What is the other cross coming from? Again, circle version of this Y. So this is Y prime. Where is the final cross coming from? This is not coming out of the bubble version. It is coming out of the regular output. So this is C in, not C in prime. So essentially, this AND gate gives you X prime, Y prime, C in. You see how to read this thing now? Is it too difficult? Be honest. Okay. So if you go through it yourself and take one input at a time and just track back, it will make sense, make perfect sense. Okay. There is nothing new essentially, except for the fact that it is a new representation that you are getting familiar with. Okay. So now if you understand this, this will be a toy problem essentially. This is essentially a very simple output that was meant to show you how this thing works. Okay. So this is the last slide of today's lecture. So we are in good shape. Don't worry. Let me stop here and see whether you have any questions, or am I rushing it? Yes.
So what's the main difference between PLA and PAL?
Yeah. The main difference is in a PLA, both the OR gate interconnects and the AND gate interconnects were programmable. So this is programmable. This is programmable. You have the option to choose how many inputs you want in the OR gate and how many, how many inputs you are going to deal with in the AND array. So this gives you more flexibility, more optimization capabilities per se in terms of Boolean logic. But on the other hand, this one is basically, for example, you already made a design decision that you have an OR gate with 4 input. Take it or leave it. If you don't need all these 4 inputs, okay, just leave the other inputs. Use the 2 or 3 inputs that you need. Does that make sense? So it's not programmable at this at the OR level. Sorry, this is not the right thing. I plan to mark this one. The OR inputs are not programmable. They are going to be fed by the ANDs anyways. So if you don't need to use them, maybe use PLA or some other, programmable logic. Let me move to this one example, this example again. So notice this was an OR gate that anyways had 4 inputs coming out of these 4 AND gates. Okay. And this OR gate also had 4 inputs coming out of these 4 AND gates. And this is a nice example. That's why I chose it. For the carry out, you didn't need one of the inputs. What do? You still have to live with this same OR gate. You don't have any choice to restructure it. You still have to live with it. You just have to make sure that you don't provide any input to this one. So it basically behaves like a 3 input OR gate, right? But you're basically wasting a, input per se. That's why I told you. And this is just a simple circuit being implemented. Imagine in a larger system, this could be even more severe, but it is what it is. You're living with a sub-optimized hardware that is giving you flexibility and cost effectiveness. That's all. Does that make sense, folks? All right. So finally, this is more like, as you see, we are going into a higher end here. One thing that I probably didn't mention. Let me see. It should be somewhere here. Yes. So in a PLA, read this sentence, this paragraph at home when you get a chance. Let me just clarify this. There are 2 ways to implement this type of programmable stuff. One is mass programmable, and the other one is field programmable. What does that mean? Mask, you don't know what a mask is, honestly, at this stage, I think. When you take 433, we talk about VLSI fabrication. Mask is essentially uh, used to create the chip. It's kind of like a blueprint of the chip, right? Mask is one of the most expensive components of chip making. You first make a mask and then use the mask to create versions of the chip, like copies of the chip. It's essentially it's like a seal that is used across thousands or even millions of designs. Does that make sense, folks? So mask programmable, meaning when you design the mask, you decide on the connection at that stage, which means you cannot change it afterwards. So imagine a certain system that you'll be using thousands or even hundreds of thousands of times. You design it at the mask level, which is the most cost effective, and then you use it. What is the difference? What is the problem there? Once you design it, you have to live with it. You cannot change it easily. You have to design a new mask. And I told you, designing a mask is more expensive, extremely expensive. Nobody wants to change a mask. Okay. How about field programmable? Fields literally talks about electric field. So you can program or reprogram this after you design the chip. So that is more flexible, obviously, as you see. If the reason why I wanted to point it out is that FPGA stands for, let me show you, field programmable gate array. So obviously it's a programmable gate which is programmable using electric field. Essentially, electric field is nothing but, it comes from voltage. So you can apply certain voltages at certain inputs to reprogram this entire thing, which is useful, of course. That's why you can take a FPGA, incorporate an adder in it, incorporate a arithmetic logic unit in it, you can incorporate a multiplexer, you could change it, reprogram it, erase it, you could do a lot of stuff, because this is, again, the term field programmable. If you change the field, the programming changes, that's all. But mass programmable stuff is basically inflexible. You cannot change the programming at all after it is designed. Okay. You might be wondering, why would you even design or use mass? Obviously, nowadays we try not to do that at all. We have FPGAs, which is on the lower end, and of course the processors are all field programmable. So we no longer have to live with mass programmability. Okay, now this is a simplified version, simplified picture of the hardware aspect of an FPGA. This is how an FPGA looks like. Notice you have a bunch of inputs and outputs. This is IO, input output block, everywhere. And inside it, this is the core component. These are called configurable logic block. So basically, these are logic that are kind of like general purpose, almost similar to what you have seen here, PLA or PAL. They're configurable, and there are different configurable blocks. So imagine this block is configurable, its neighbor is also configurable, and you can use them in unison. The interconnect between these two blocks is also programmable. So there are multiple levels of programmability. So you have, are you still with me? Don't give up. Okay. I know it's a mouthful because we don't see the lower level view in this course. If you take a computer architecture course or something, they typically get into the details of it. But given the time, obviously, and the amount of syllabus we have to cover, we have to learn a little bit about many topics in this course, not a lot about one topic. So for that, you have specialized courses. For example, if you take computer architecture, it gets into the depth of the architecture itself, rather than showing you all sorts of keywords that you're learning in this course. So the purpose is different. So don't feel like, oh, I mean, there is no way for you to know this. Of course, you have a long way ahead of you. You can definitely go deeper into any of this direction, depending on what interests you. But my point is, the picture that you're getting here is a very high level conceptual picture of an FPGA. So this is essentially a black box. Within it, there is a configurable logic block. So you can reconfigure this block like you have seen for the PLA or PAL. This is reconfigurable. But then imagine you have one reconfigurable block here, you have another reconfigurable block and another reconfigurable block around it. And the connection between these blocks, like this, are also configurable. So that gives you tremendous power, because now you can incorporate more complex logic. You see that? With one configurable logic block, yes, you can incorporate certain functions, but when you have multiples that can also be connected with each other in certain ways, that gives you more complexity. So it's basically approaching the complexity of a conventional processor, microprocessor, by, essentially there is a name, although in your textbook they call it interconnect area. So in between these blocks, you have just metal lines going from one block to the other, just metal lines, that's all. Zigzag wires, essentially. Of course, we don't just randomly route them. We have horizontal and vertical routing. And also, there is a very important component which is not part of this course. It's called switch matrix. It's an important part of FPGA design, switch matrix design. So what it does is, so basically you have, say, horizontal and vertical interconnect. It decides which line will be connected to what. Say, will you connect it this way, or will you connect it this way? So essentially it's like rerouting a train line, right? You could use the same track, but you can route the train in different direction by changing some, components. So that's what the switch matrix does. It connects different components in certain ways based on the programming. So what you do in FPGA programming is essentially you program the switch matrix. You don't really change anything honestly inside this ones. You change the switch metrics to make sure you incorporate different logic function. Now, look at the best part. When you design and when you use your FPGA board for this course, you will be oblivious to this deeper level hardware detail. You just run a code, you write a code and run it, and it behaves like an adder. It behaves like a multiplexer, basically. So that's the power of levels of abstraction. They don't make you go through that degree of detail if you don't have to. But if you want to get deeper into this, how are they exactly mapped in the hardware? You have the option to do so, right? So that's basically what FPGA is on a higher level, and that is deliberate. And you will have some experience working with FPGA, as you know, in this course. So with that, that concludes this lecture. We'll start fresh in the next class with a new topic, all right? Thank you.